Welcome to section 11.5, area of regular polygons. Today we're looking at two special polygons, the regular hexagon and the equilateral triangle, and seeing if there's a specific formula we can use to calculate the area of each. We're going to start off with the equilateral triangle, and the equilateral triangle has the formula s squared divided by 4 times the square root of 3, where s is the side of the equilateral triangle. So effectively what we're going to do is we're going to take that side, multiply it by itself, divide by 4, and then multiply by the square root of 3. Now if we get a nice number, we can easily divide it by 4. If it's something that we need to simplify a little bit further, we'll simplify where necessary. So looking at our first example, we have the area of this triangle that's listed out here. This is example number 1. We're going to find the area of the triangle that's equilateral with side 8. So we're going to plug it right into our formula, s squared divided by 4 times the square root of 3. So we'll square 8 and get 64. That's where we get this number right here. Divide that by 4, which will become 16. And our final answer for the area of the triangle is 16 times the square root of 3. Now, if we needed to, if we forgot the formula for some reason, we could draw an altitude into here. These angles at the base would be 60 degrees. We know that the altitude in this triangle will divide that 8 into 4 and 4. So we'd have a 30, 60, 90 triangle with a side of 4, and then it would have a height of 4 root 3. So we could do 8 times 4 root 3, which is 32 root 3, and then take half of that. So in a pinch, if we don't remember the formula, we can still use 1/2 base times height. Here's another example of an area of an equilateral triangle. In this case, we're given that the height is 6 root 3, so we have that information already. We're going to take that information to find out what the base is. Now again, we have a 30, 60, 90 triangle set up, so these base angles here are 60 because in an equilateral triangle, all the major angles are 60. And then from there, that's my x root 3. The side across from the 30 is my x, and the hypotenuse is my 2x. The hypotenuse in this case represents what the entire side is. So the side is 12. I can plug it right into my formula. 12 squared divided by 4 will eventually simplify down to 36 with the square root of 3. If we did it the 1/2 base times height method, we would have a base of 12 and a height of 6 root 3. Multiply those together and you get 72 root 3. Take half, gets you 36. Same result, different method on how to solve it. Alright, the next thing we need to talk about is an apothem and perimeter, because that's going to lead into the hexagon formula. An apothem is a segment joining the center of a regular polygon, so right in the middle of that shape, so in this case that is point O, to the midpoint of an opposite side. So A is the midpoint of this side down here at the bottom. And what that means is it's going to divide the segment into 2 equal pieces. So this segment right here and that one right there. And it's also perpendicular to it, so it is a perpendicular bisector. A radius of a regular polygon connects the center to the vertex. So it goes from the center to the corner. OA is the apothem and OB is the radius. The reason we need to know this is in a regular polygon, the formula for the area is 1/2 the apothem times the perimeter. Again, the perimeter is all the sides added up, and the apothem is just that segment that goes from the center of the polygon to the midpoint of the opposite side. So in an example where I don't tell you what kind of polygon it is, but I say here's the apothem and the perimeter, it's a direct application of the formula. We say, alright, the area is 1/2 AP, so it's 1/2 the apothem, which is 8, times the perimeter, which is 20. 8 times 20 gives me 160, and I take half of that and I get 80. Now the area of a regular hexagon, it's one of the more challenging things in the chapter. There's really no doubt about that. Part of the issue that we have is we have to find two not quite easy measurements. One of them is the apothem, and then one of them is the actual perimeter. The perimeter is fine once you know what one side measures. Now in a regular hexagon, we have 6 sides. Our key here is to be able to find out what one of the sides is. Now what ends up happening with a regular hexagon is we have a 30, 60, 90 triangle set up, because this apothem is going to be perpendicular to the side. Down here, this entire angle is 120, and that radius will divide it into 2. I know it's 120 because of the formula that we had from chapter 7, where we can take the sum of the interior angles and divide by how many there are. N minus 2 times 180 divided by n. And it tells me what each interior angle is. But again, that radius is going to divide it by 2. It's 60 down here, and then we have a 30 here. Now, if you set this up right, if you set this diagram up the same way every single time, here's how you can remember where the 60 goes. It is heavier than 30. It sinks to the bottom, and the 30 floats to the top. If you can remember that, then you can easily solve apothem problems. So I have my x root 3. I can find my x. It's the one across from 30. My entire side is 6. So I take 6 because that's what each side is, and there are 6 of them. So I multiply 6 by 6, and I get 36. That's my perimeter. My apothem was given to me. It's 3 root 3. Sorry for the bell there. We take apothem equal, or area equals 1/2 the apothem, which is 3 root 3, times the perimeter, which is 36. Multiply those two numbers together. I get 54 root 3. I take half, or sorry, 108 root 3, and I take half of that, and I get 54 root 3. That's the area of a regular hexagon. Now, there is another method we can use, and I'm going to show you that in class, where we can actually divide that hexagon into shapes that we already know. And whichever method works best for you, use it that way.